In our world of today, AI has become a norm. AI is everywhere, and new AI models get developed and deployed more frequently than not. In this video, we are going to learn how to use already trained AI models, fine-tune them to perform tasks that we want, a concept we call transfer learning. My name is Dennis, and welcome to my YouTube channel. Here is a visual depiction of what we are going to build. We'll be using VGG19, which is a CNN, convolutional neural network, that was trained on the ImageNet dataset. The ImageNet dataset contains a lot of images, which means this model, VGG19, has knowledge of a lot of images since it was trained on the ImageNet dataset. What we'll do next is remove the base model's fully connected layer and output layer. Build our own fully connected layer and output layer. Basically, everything from this end to that end, in what we call feature extraction. We will come back to this in the future. Also, for the fine tuning, we are going to freeze and unfreeze certain parts of our base model, which means we will train our dataset on some parts of the base model plus everything we will build here to then make a prediction. One thing you'll notice is that the dataset we want to use for our fine-tuning, CIFAR10, has 10 classes, meaning it makes predictions on 10 items: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. Which means at the end, when we feed an unseen image, an image our model has never seen before, of any of the classes, airplane, automobile, cat, dog, our model should be able to predict with a good probability that this image is a dog, an airplane, or an automobile. That is the goal. Here we take a look at our dataset, the CIFAR10, which consists of 60,000 32 by 32 colored images in 10 classes with 6,000 images per class. This means that the dataset consists of 60,000 images, and each image has a height of 32 and a width of 32, and they are colored images, which means they are of RGB. Almost every color can be obtained from RGB, which is red, green, and blue, in 10 classes with 6,000 images per class. There are 50,000 training images and 10,000 test images. So out of the 60,000 images that we have, we are going to train our model on 50,000 of them. And the remaining 10,000, we are going to test them on our model to see if our model, after the training, is able to predict correctly the classes that we have. If we test it with any image from any of the classes, whether it's able to predict accurately that this is an airplane, this is a cat, or this is a dog, or this is a frog. So that is why we are going to do 60,000, 50,000 for training, and 10,000 for testing. We have the various classes here and sample images also down here. The link to this page is in the description. Now, since we'll be using TensorFlow, I thought it wise to also let you know that CIFAR10 is actually available on TensorFlow in the datasets catalog with, the same information, 60,000 with 50,000 training and 10,000 testing images. And the homepage, the page we were on before, the link to the homepage is actually available here. Our next stop is on the already trained AI model we'll be using, in this case, VGG19. Now, VGG19 is what we are going to use as our base model because it is already trained. So again, VGG19 is also available on TensorFlow, which we will be using. And just a little bit about VGG19. So we can see here weight equals ImageNet, meaning it was trained on the ImageNet dataset. Its knowledge, which is its weights, are from the ImageNet dataset. We have classes here as 1000, meaning it was trained to make predictions on 1000 classes. But that is something we are not interested in. We are only interested in making predictions on just 10 classes using a different dataset, which is the CIFAR10. And the classifier activation is softmax. So later in this video we will talk about the softmax activation function, which deals more with the latter part at the output layer. So link to this will be in the description. So I created a notebook in Google Colab called CIFAR10 Transfer Learning. In order to implement this project, you are going to need a GPU. Now I understand most computers come with CPUs. Now to train this model on a CPU will probably take some days or even a week. But with a GPU, it could take probably around 20 minutes to finish training your AI model. Since the datasets we are going to use are pretty large, as I showed you before, that is why we require a GPU, not a CPU, since a CPU will be very, very slow. But there is some good news. Whether you have a CPU, a GPU, you can just go online, go on Google Colab, create a notebook, and there are some free GPUs you can use in here in Google Colab. Of course, they are limited, but they are free. Now, we are ready to build our model. But first, we need to grab some tools which we will use to build the model. So in our first chunk, that is what we are going to do. We are going to be grabbing all these tools. So I'll start with the first one, which is TensorFlow. As TF. And also from the same TensorFlow, the keras.applications, I'm going to import our model, which is VGG19, and I'm going to copy these guys. No, I'm going to copy from here, just copy this guy here, and then just move it to the next line and paste, because I'll be grabbing more things from TensorFlow, the keras. So the next thing I'll be needing is my dataset. So I'll grab my dataset, which is CIFAR10. Then next up is I'll paste again and get my models. Now this model is going to be the fine-tuning model we are going to build. So that is why I need this model in here. The next thing I'm going to grab again from TensorFlow, the keras, is going to be our layers. Now remember that we were building our own output layer or our fully connected layer, and for that I will need layers to do that. So I'll import dense, you have to import global average pooling, pooling to the, and I also need some dropouts to control overfitting. The next thing I'll do again from keras.tensorflow, I'll need to optimize my model. You know our model will definitely make errors during the training. So to do that, I will need to optimize it along the way. And for that, I will need some optimizers. One popular one we know is Adam, which I'm going to use in here. So again, from TensorFlow, keras.optimizers, I'm going to import Adam. The next thing is, because I'll be dealing with images, I'll need to include some image processing. So processing.image, I'm going to import some image data generator. The next thing I'll need is, computers actually do not understand like dog, cat, they actually understand numbers. So we need to convert our actual values, which are our y values, to categorical values, something we call one-hot encoding. Don't worry about this. As we go along, I'm going to explain what all these things are. So you get to understand them when we use them. So don't worry about it right now. So I'm going to import to categorical. Then because I'll be at the end of the training, I will need to know how well my model is performing by comparing the the curves of the training data and also the validation sets. I need to see how well my model is performing from the training to the validation or the testing to see whether it's overfitting and even the accuracy of my model, because I need to test the model after I trained it. Okay, so I need to know the accuracy, and I need to do this on a plot. So to do that, I will need to import I need to use matplotlib to do that. So I'm going to import matplotlib to do the plotting. So import matplotlib.pyplots as PO. So I'll take this. All right. So we started with importing TensorFlow, and then we got with getting our base model, which is VGG19. We also imported our data set, which is CIFAR10. Because we're building our fine-tuning model, I imported model. Because we'll be building a fully connected layer and our output layer, and also to control overfitting, I got my layers in here. To control the errors that our model will be making, or to optimize my model more, I included the Adam optimizer from Keras optimizers. And also, because we're working with images, to do some data augmentation, I included image data generator. And also, because we want to use one-hot encoding for our softmax activation at the output layer, which I will explain later, I included from the utilities to categorical, and lastly to plot and to see how well our model is performing against the validation set or the test set or the test images. I needed to plot it on a graph. That is why I imported matplotlib.pyplot as PLT to do that. So I'll just give a comment here and say this general imports. Yeah. So what we're going to do next is, if you remember, I talked about the fact that we do not want to run this on a CPU. We want to use a GPU, and Google Colab, with the good news, provide us with a GPU. So to use our GPU, we kind of go here, and then we choose change runtime type. Now over here, we change it from CPU to a GPU. All right. And then we go to save. And now after it connects to the backend, what you do is here, you come here and then you run from here. In the next chunk, we are going to create a function to load our data set. So def in Python load dataset, and then we pass in the dataset name. So you say load if dataset name equals CIFAR, then we are going to create a tuple that's going to receive the training dataset and the test dataset. So we create a tuple here and give it xtrain and then ytrain, and another one for the testing. So xtest ytest CIFAR10 dot load data. Alright, so what we did here was that we loaded the CIFAR10, which we imported from up here, and then we loaded it into these tuples, and we divided it into the training and the test, just as we saw from the documentation, that some parts is going to be for the training and another part is going to be for the testing. Now the reason why you have x and y here is that the x train here is for the training values, and then the y train will be for the actual values that we want we want the model to be able to predict. Then this is also the same thing for testing. We have the x values and then we have the y values. The x values are what we will feed to the model, and the y values are what we expect the model to produce or to predict. So the same thing for the training and the same thing for the testing. Now we know that for the CIFAR10, it has a number of classes to be 10. So we set the number of classes to 10. And I think we can just else, and in case there's something else, like you can raise a value error and say dataset is not supported. Yeah, something like this. Then once we have our dataset loaded, which is we have our training and we have our testing, we want to perform some data processing on it. So data pre-processing. What this means is that pre-processing, we want to do some preparations with the data before we feed it into the model. So to do that, I'll explain this as we do it. So we have xtrain and we have xtest. Now what are we going to do to them? Let's see. I'm going to divide it here by 255.0, and also I'm going to take the xtest and also divide it by 255.0. Now what am I doing over here? So we know that the pixel values in an image ranges from 0 to 255, which is 255. Now, to better make our model train well, we want to ensure that the pixel values in the images are within 0 and 1. And to do that, we are going to divide the pixel values in the image by 255, which is the highest pixel value, to ensure that all the pixel values in the images are within 0 and 1. This is a very good practice. That is why we also implement it in here as part of data processing, data pre-processing. The next thing we're going to do is on the y values. So we take y train, and I'll say y train equals to categorical. Do I have it? Yeah, to categorical. I'll pass in the y train value and the number of classes. I'll explain this also. So I'll take another y test, right? And then again to categorical. To categorical, I'll pass in the y test and the number of classes. Now, what am I doing also with the y values? Now, as I said before, we want to do something called one-hot encoding, because our model actually does not know door, cat. It doesn't read that way. It actually reads numbers. So we need to do this one-hot encoding to ensure that we are passing the right thing. So let me show you how the one-hot encoding actually works. So over here, if you take a class or if you take an image of an airplane, right, and we do to categorical, if you remember, to categorical here is from the top. We imported it from TensorFlow.keras.utilities. It's part of the utilities. So to categorical, we perform it on the y train. So remember, we have the number of classes for the y train. We have 10 classes. Okay, so if you pick, let's say, an airplane, to categorical is going to take the first place in the class and assign it the highest value. So the highest value in this case is going to be 1, and all the other classes is going to be 0. So to the computer, this value here, this vector here is an airplane. The same thing for an automobile. The computer, this is how it is what an automobile is. The first place is 0. Now an automobile is in the second space. So the second space is assigned the highest value, which is 1. And all the other classes are assigned 0. And this applies to all the other items we have: bird, cat, deer, dog, frog, horse, sheep, truck. So you can see that for the truck also, the last place is assigned the highest value, which is 1, and all the other classes have 0. So this is what the computer actually sees as a truck, this vector. Now, another thing you will realize when we get to softmax activation is that in here, with the one-hot encoding, you realize that the sum of all the values in the vector is actually equal to 1. And that 1 is assigned to the class, which represents airplane. The same thing for automobile. The sum here of all the values here is 1, which is the highest value, 1, and that 1 is assigned to the second class, automobile. So the same thing with the softmax activation. But when we get there, I'll explain it better. But for now, just try and understand the one-hot encoding. That this is how the computer understands what an airplane is when we apply to categorical to the images. So for an airplane image, the computer sees it this way. And for an automobile, the computer sees it this way. So the highest value in the vector is assigned to that particular class. Alright, so that will be it for this one, the one-hot encoding. So we come back here. and then we return, of course it's a function, so we want to return something. We want to return the X train, the Y train, so our training set, then the testing set, X test, Y test, and the number of classes, right? So this will be it for our function, which is going to load the data set. So we know what data set we are working with, which is CIFAR10. So if the data set is CIFAR10, then we want to load it into the train and in the test. And then we know the number of classes to be 10. Else, then that data set is not supported for our model. Then we perform some data pre-processing, which is we ensure that the pixel values are within 0 and 1, which is by dividing the pixel values by the highest pixel value, which is 255, for the X train and the X test, because these are what we'll be feeding into the model. Then for the Y values, we want to ensure that the computer knows what each class represents, which is what we did with the one-hot encoding, that the highest value is assigned to one particular space, which represents the class. So it puts 1 over there for that particular class, in any other space is 0, as we saw before. And then finally we return our X train, our Y train, our X test, Y test, and the number of classes. So that will be it for this chunk. So you can run it and we move to the next. In our next chunk, I'm going to create a function for training our model, since we are done loading the dataset and pre-processing it. So I'm going to create a function in Python def and train model and pass in the dataset name. Okay. Now, before we continue to build our function for training the model, let's take a look at our diagram. So to train the model, we will need an input, and then we will need the base model. So let's start with these two, and then we proceed from there. So the first thing is that we are going to need an input, which in this case is going to come from our CIFAR10 dataset, and then we're going to need a base model, which in this case is supposed to be the VGG19. So let's do just that and come back. So over here, as we said before, we will need an input which will come from our CIFAR10. So we are going to need to load this dataset. Okay, so we are going to use, I can actually use the same variable names. I can copy here and paste, and then set, and I'm going to load dataset. Okay, and I'm just going to pass in the dataset name. Right, so now we have our input. The next thing is to get our base model. To get the base model, I'm just going to do base model equals, now remember that we have imported VGG19 already from Keras applications from TensorFlow. So I can just go here and do VGG19, which is the name of our base model. And then VGG19 has knowledge from ImageNet, so I can do width equals ImageNet, and then I'm going to do some few things here and explain later. I'm going to give it force, and then give an input shape of 32, yeah, 32 and 32.3, yeah. Okay, so I'm just going to create a new chunk here, copy this guy, paste it in here. No, this is not what I'm trying to do. I just want to create a chunk here, paste this guy here. Okay, and let's try and see the base model. How does this base model actually look like? Okay, so we want to do a summary of our base model. All right, so to make some few changes, let's make this to be, let's say, true. Okay, and then let's remove this actually, just to make the explanation better. So first of all, we had our inputs, the information we're going to input into the training into the model, and then we need the base model, which is VGG19. But before we continue, I want us to see how VGG19 actually looks like, okay, before we proceed. So let's run this chunk. Good. So this is the summary of VGG19. So you can see that VGG19 takes an input that has dimensions of 224, 224, and they are colored, okay? And then you can scroll down and you can see that the last part here, we have a black pool, max pooling 2D, and then there is flatten, dense, 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 and then mixed predictions. But you can see that for the predictions, this base model makes predictions of 1000. Okay, this is something we do not need. We only want to make predictions of 10. Okay, so what we're going to do is that this top, from this part here, the flatten, to the predictions here is what we call the fully connected layer. So for that part, we are going to build our own. So if you remember from the diagram that I showed you, from this 1D vector, the 1D vector is what we have here, max pooling 2D, sorry, the flatten. This flatten here, it flattens everything, it flattens everything from this max pooling into one dimensional vector. So it flattens everything into a one-dimensional vector, and this one-dimensional vector is fed into the fully connected layer. So in this case, after it flattens it, it feeds that one-dimensional vector into the fully connected layers we have here, which is these two dense layers, before it makes a prediction on 1000 classes. As I told you, we only need 10 classes. So we are going to do that. We're going to remove this here. We have to remove it so that we can build our own fully connected layer and our own output layer to make our own predictions on just 10 classes. So to do that, we will do something here with the include top. So that part is what we call the top. So we are going to say, to include the top, you say false. Okay, so this means that it should not include the top. So if I run the code again to see that base model, you can see that over here it ends at the max pooling. There is no top. You can see that there are no predictions anymore. It has removed that part. So it means that now we can build our own fully connected layer and our own output layer over here to make our own predictions. Okay, so that is one thing. And again, the input shape. Now remember that VGG19 was trained on images with dimensions of 224, as we saw before. But our input shape, we are taking 3232, 3232. Now this is for some reasons. Because of resource constraints, we are not going to resize all 60,000 images. We are going to use the images as they are, and I'll explain why as we go along, just because of resource constraints. Okay, so we are going to, so this explains the code over here. To include the top, we see it false, so that we can build our own fully connected layer and make our own predictions. And also our input shape, that means for the input layer, the images you are going to feed into this base model are going to have a shape of 32, 32, 3. If you remember from the CIFAR dataset documentation, it talked about the fact that the dimensions of the images had a height of 32, a width of 32, and they were colored, which means RGB. And RGB is what this 3 means for R, G, and B. Okay, so that is for this part. Now, still inside our train model function, I'm going to say base model dot trainable equals true. Okay, now you can see from the summary of the model VGG19 that we have lots of layers. So I'm just saying that the entire model should be trainable. We should be able to update the weights. Now I'll explain more later. Let's go back here and see something. We worked on the input and we worked on the model, right? Now, if you come down here to the fine-tuning part, this part is that with the given base model, we want to be able to freeze some layers and train some layers. Okay, so if you can see from here, there are so many layers in our base model. We want to freeze some of them and train our model on some of them. Now you know that this base model knows a lot. It has a lot of knowledge from its previous training. So we want to keep some of them. And then from the data that we are also going to train on top of this, we want it to also learn from the CIFAR10. So keep some of the previous knowledge it had from the ImageNet, and also we train the remainder of the layers on the new dataset, which is the CIFAR10. Too much talking. Let's do something here. So here I'm going to do something. I'm going to say for layer in base model dot layers, and then I'm going to do something we call slicing and do -15 here. Okay, and then I'm going to do layer dot trainable equals false. What this code means here is that now this negative value here is purely experimental. What I mean by experimental is that I didn't know it beforehand. It's a value you just test out to see whether it works. Okay, you know, the majority part of AI is experimental. There are some values we call hyperparameters. You do not know them beforehand. You test some couple of values out and then you find a value that will best fit your model. So you don't know them beforehand. You have to test them out in order to know them. So I am picking -15. So what this means here is that from the first layer to the layer before the rest of the 15 layers. So for the initial layers, that is, let's say from 1 to the 5th layer, I want to freeze them. So layer.trainable equals false. I don't want to train them. If I don't want to train them, it means I want to freeze them. So let's say for the first 5 layers in here in the base model, I am freezing them. But then the last 15 layers, okay, I want to be able to train the last 15 layers. So that is what this slicing here does. So if you come back to that diagram, we have some layers in our base model. And then what we are doing is that we are freezing some of the layers and then we are training some part of it. So what we are doing is that we are retaining some of the knowledge from the previous data set that the base model was trained on. And then another part of it, we are going to train that part on the new data set. So it's going to be, the weights are going to be updated. It will learn from the current data set and its previous data set. But for the frozen layer, it only knows its previous data set. Too much talking. Let's come here. So that is what we are trying to do in here. Base model.trainable equals true to be able to train my entire data set. But no, I don't want to train the entire base model. I want to just train a portion of it. That is the last 15 layers of it. So I freeze the initial part of it, and then the last 15 layers I keep them as the last 15 layers I train them. You freeze the initial part, you train the last 15. That is what this code means. So we've been able to implement the input, the base model, and in the fine-tuning part. Next, we create a variable called x, and we take a look at our diagram again. Since we completed this portion, it means that we are here now. We need a one-dimensional vector that we can feed into a fully connected layer. So to do that, one technique that is mostly used is what we call the global average pooling. Remember, we got it from here, the global average pooling 2D. So that is what we are going to call. So we are going to use that instead of the flatten. So I'll explain that. So global average pooling, which is 2D, and then we apply that. We are going to apply this on the base model. The output, that is the output of the base model. So I'm going to explain this part. So if you remember this model from VGG19, you remember that when VGG19 got to the max pooling 2D, what they did is that they used a flatten. Now, if you have a very large data set and you flatten the data set, you are going to get a one-dimensional vector that is very, very long. So to prevent this, we use what we call the global average pooling. What this global average pooling does is that it finds the average between, or it finds the average of your feature maps to construct this here, which will be fed into the fully connected layer. Okay, this is way better than using flatten. And now remember that we are going to perform this 1D vector. We are going to apply it from here. So we got the fine tuning, and then which is the fine tuning from the base model. We are going to supply that to this 1D vector. Okay, so if you come here, what we did is that we had a global average pooling, and then we took the output from the base model. Remember, what's the output from the base model? This will be the output from the base model. We are taking the output from the base model. Okay, just like from here, we take the output and then we apply it to get a 1D vector. So that is exactly what we are doing. We are taking the base model output, the output, and then performing a global average pooling on it. Next, again, we take X, and what we're going to do is that we are now going to build our fully connected layer and our output layer, because now we have our 1D vector, so we can perform some operations to get our fully connected layer and our output layer. So that's what we're going to do now. So from here, I'm going to create dense. You remember I imported dense from here to create a layer, if you remember from Keras. So the same thing. I think I can delete this from here since we no longer will need it, so that we can focus just here. Okay, so we get a dense, and then I go, let's try 256 filters or kernels and an activation. Our activation, we're going to use Relu to introduce some what we call non-linearity. And we are going to perform this on this layer. We have done this one, right? We've done an X. So we're going to perform, or we are going to, you can see they are all connected. From the 1D, then the 1D is fed into the fully connected layer. So now we've built our first layer, which is going to take from the 1D vector, right? So we had the 1D vector here, and then we are going to feed that one into this dense layer, so which is the X we have over here, right? Then next is we perform some what we call dropouts. This dropout is mostly to prevent overfitting. So it intentionally drops some of the layers just so that our model does not learn some complex training, and it doesn't generalize poorly. I'll explain this one also better later, but the whole point about dropouts is to prevent overfitting. So when we get to the latter part, you understand what overfitting actually is. So we do dropout. Remember that I already imported dropout from the top because I knew I'll try to prevent overfitting. So I got dropout, and I'll give it a value of, let's say, half, 0.5, right? And then again, we apply it on the previous layer, which is X, right? We are on the previous layer, this layer here. Then next, I think I'm going to just repeat the whole thing again. So I'll just copy and paste. Then I'm going to change the number of kernels here. And remember, the number of kernels are always multiples of 2. So 2 times 256 is 512. So you just increase it, multiples of 2. I'm going to use the same Relu activation to introduce some non-linearity into our model. And then the same drop half of it, which is 0.5 of the layers, apply it on this layer, which is the same X. Then the last one will be, the last one will be our output layer, which determines the number of classes. So with the output layer, again, I'm going to take an X and say a dense, and I'm going to specify the number of classes, which I have already indicated. And then the activation. Now notice the activation here, which is going to be quite different. This one is going to be what we call soft max activation. Okay, and I'm going to apply it from the previous layer, So I give it an X. So now let's explain what we have actually done here. So we got a one-dimensional vector using the global average pooling, which will take the average of each feature map. Okay, I'll explain feature maps to probably in the comment section, but let's focus here now. So with the one-dimensional vector, we get the averages of all the feature maps into a 1D vector. Now we apply this on the previous, okay, we get this 1D from the previous layer, which in this case will be the output of our base model. Remember, we are coming from the base model. This is the base model. We are coming from the base model, so we need the output of the base model to apply to get our one-dimensional vector, which is exactly what we did here. The base model's output, we store that in X. Then now we build our fully connected layer, which has 256 kernels. Remember, these values are fully experimental. In my case, you can try your own number of kernels. I told you AI for the most part is somehow experimental. You need to try some values out to see how it affects your model. Then for the activation, I'm going to introduce nonlinearity using the ReLU activation function. And I'm going to apply this from the previous layer. So I'm feeding this into this layer. That is why I bring the X in here. Then for the next layer, I have a dropout, which will introduce what we call, which is to prevent overfitting. So it is going to drop 50% of our layers so that our model does not learn complex and noisy patterns, but then is able to generalize properly. Okay. And then the next one is another layer called a dense layer, which also has more kernels. And I told you before, the kernels are mostly multiples of 2. And then the activation again, and then we apply it from the previous layer. So we feed it into the next layer, which is the same X. Again, apply some dropout to prevent overfitting. Then the last layer here is going to be our output layer, which is dense. Then the number of classes, which we know we are expecting 10 classes. We've already specified this when we're loading our data set. And then we are going to use something we call softmax, and then we will apply it from the previous layer. So now let me explain what the softmax actually is. So let's come down here. You remember when we were talking about the one-hot encoding and that we put the maximum value, which is 1, and all the remaining values are 0. The softmax actually also has that kind of, if you have the idea in mind, the softmax should be very easy for you. So what the softmax does is that once we feed an image into the model makes a prediction, which is in the form of probabilities. And this probability is obviously from 0 to 1, 1 being the highest value. And the model predicts with what percentage this image falls in either of these categories. So it says that if, for instance, I feed it an image, it says that this image has a 1% chance of being an airplane. It has a 0% chance of being an automobile, 0 for being a bird, 1% of being a cat, 0 for being a deer, 0 for being a dog, and then it has 80% of being a horse, 0% of being a ship, and 0 for being a truck. So what this means is that our model is saying that the image we fed into the model, it is predicting using a softmax activation function that image we fed into our model has an 80% chance of being a horse. If you remember from the one-hot encoding, the reason why we are saying this represents a horse is that from the one-hot encoding, the place with the highest value in the one-hot encoding was this place, the 8th place had 1 for the horse. So 0, 0, 0, 0, 0, and the maximum value was 1. Remember, for the softmax, if I combine all these values here, I'm supposed to get 1. If I add all these values up, I'm going to get 1. If the same thing for this horse, if I combine everything, I'm going to get a 1. And then the place with the highest value is this place, which is the 8th place, which has the highest value 1. The same thing for the softmax, the place with the highest value is the 8th place, which is 0.8. So our model is telling us that the 8th place, which represents the 8th class, and we know the 8th class is a horse. So our model is saying that the image that we fed, which is an example, the image that we fed into the model is a horse. So we can take this that the image we fed into our model is a horse. That means it has an 80% probability of being a horse. So the image is a horse. This is how our model actually works. And this is how softmax activation actually works. It finds the probability for each of the classes. That what is the percentage of this, or what is the probability of this image being any of the classes, an airplane, an automobile, and it gives it values. And these values sum to 1. And then the one with the highest value becomes what our model will predict. So in this case, it's going to predict that the image we fed into the model is a horse. And it can change for any other class. So that's how it works. So that is it for the softmax activation. This is basically how the softmax activation works. Good. So now we've been able to build input base model. We fine-tuned it. We got a 1D vector. We had a fully connected layer. We had an output layer with the number of classes. Now what we're going to do is that now we have to combine everything together and get one fine-tuning model. Okay, we have to combine everything together. We use the output from the base model to get our 1D. We built our own fully connected layer, got our own output and the classes. The final thing to do now here, in respect to this, that we need to build our own fine-tuning model. So I'll go back to the code here. And this is what I'm going to do. I'm going to say fine-tuning model equals, remember I told you we are going to build a fine-tuning model. So I imported model from models in Keras from TensorFlow. Okay, at the top right here. So we are building a fine-tuning model which will combine the base model and the output layer that we, or the fully connected layer that we built. So the first thing is that it is going to take the base model as input. So we say input equals base model dot input. Okay, then our output is going to be just X, as we did here. So what this thing means is that we've created a new model called a fine-tuning model. And this model, just as we have in the diagram, is taking this base as its input. Okay, this side as its input. And the X part that we built, this part will be the output. So this will be the part that does the prediction. So that is exactly what we have done here. Fine-tuning model, we have our inputs and then we have our outputs. That is it for this part. So we said our model is going to make predictions. And if it's going to make predictions, we know we are training the model. So if you are training the model and it's going to make predictions, obviously it's going to make errors. One thing we want to know is that we want to measure our model's accuracy. We want to know the errors it is making. And we want to optimize our model based on this error so that we can improve the model. So in machine learning, this is what we call compiling. So I'm going to do fine-tuning model dot compile, right? And inside this compile, that is where everything happens. You remember I talked about optimizers, right? So I'm going to use the optimizer I called on top here, called Adam. We know this guy called Adam. He's one of the optimizers that we are going to use. So we call Adam here. And then we are going to do something we call learning rate. So I'm going to give a very small learning rate. Now you remember when I talked about hyperparameters, that in machine learning, for the most part, we have lots of experiments. And these things are, for these hyperparameters, they are very experimental. You do not particularly know the value, you just have to test out a couple of values and then you see how it fits your model. But generally speaking, these experimental values, whenever you are using them, you want to start very small. That is why for the learning rate for the Adam, I chose something very small, like 0.0004, a very small value. Then for the loss, I'm going to do something called categorical cross entropy. I mean, it's a mouthful, but that's categorical cross entropy. That is right. And the next thing is the metrics. As I told you before, we are going to measure its accuracy. Okay, so to kind of talk about this compiling here, what we wanted to do is that we want to measure the accuracy. Now, in machine learning, there is this concept called stochastic gradient descent. So as our model makes errors, okay, as it is being trained and it makes errors. What you want to do is that once it makes an error, the error that it made, so let's take it this way. Our model will make a prediction. The difference between the prediction that our model made and the actual true value, the difference between the prediction that our model made and the true value, the difference between them is the error. So that is the error. Now, getting this error, we are going to find the derivative of this error with respect to the weight of our model. I know that's a lot, but I'm going to break it down. Now, when we find the derivative of this error that our model made with respect to the weight, this is going to help reduce the error that the model is going to make in the next training. So what is happening is that we use the error that the model will make to correct the training, so that the next training it reduces the error, or the error reduces. So let's take a value, say x squared. If I find the derivative of x squared, I get 2x, right? Now x squared, if let's say the value of x is 5, x squared is going to be 25. Now if I find a derivative of x squared, it becomes 2x. Now what is 2x? 2x is 10. So you can see that the value decreased from 25 to 10 after we found a derivative. So you see the value is decreasing. The same thing with the loss we are doing over here. Once we're able to find the loss, which is the error, which I define that the error is the difference between the predicted value and the actual value. Once we get this error and we find the derivative of this error with respect to the weight of the model, we are able to reduce the error, so that in the next training, with the updated weights, the model is able to predict better. And then we find the error again, we update the weight, then the model predicts better. So in each training, the model gets better using its own error. That is what we are doing here. Okay, so that is basically what this compile does. We have the Adam optimizer, the loss, and the metrics all helping in that. That is basically the idea here, to ensure that our model gets better in each training. Okay, now next, what we are going to do is what we call data augmentation. Now imagine we are feeding our data with an image of a cat. Now the cat is sitting down. If we rotate the image, will our model still be able to predict that this image is an image of a cat? So this is where data augmentation comes in. With data augmentation, we are going to be rotating the image and be doing all kinds of stuff to the image, so that no matter which angle the image is positioned, our model will still be able to predict that this is an image of a cat. This is data augmentation. So let's do that. I'll do something called data gen, okay, and set this to be, remember I imported the image data, if I could type it, generator in here, then I'm going to say rotation. So if you rotate our image by, let's say 15 degrees, okay, and the width, let's say the width shift range, let's say 0.1, that's, let's say 10%. So if we randomly shift the image, that is if we randomly shift the image horizontally by 10%, our model should still be able to predict. So the next thing we are doing here is you do height, that is for the vertical shift, and then I'll do range the same, let's take 10%. Then I'll say horizontal, let's say flip. So now if I even flip the image, let's set that to true. I think capital will do. Yeah, let's get rid of this. Yeah, so let's take a look at it again. We are talking about data augmentation. So in here, let me put a comma here. We are rotating the image we are going to pass by 15 degrees. We are also randomly shifting the image horizontally by 10%. All right, we are also vertically shifting the image 10%, we are also flipping the image horizontally. Okay, so we are setting it to true. This is all to help reduce overfitting so that our model will still be able to predict the image no matter how they are oriented. Okay, to just produce or to reduce overfitting. Let me just put it that way. So finally, we say data gen.fit. This is very important. X-train. So we are going to perform this on the training dataset. Just the training dataset. All right. So once you are able to do this, the final thing we can do now is to now train our model. We know we've been talking a lot about this, build the base model, fine tune it 1D, build a fully connected layer, it makes predictions. Now it makes predictions, it makes errors. We talked about data augmentation, which can help prevent overfitting, and also the fact that we want, no matter how the image is oriented, our model should be able to predict it. Now, we've talked about everything. Now, the main thing we have to do now is to actually train the model. You see, we've talked about building stuff, but we have not actually trained the model. So to train the model, that is what we call fit. Okay, so we come down here. So we are still inside our function. Okay, still inside our train model function. Okay, and then we call, let's say, history. Let's say history 1. I'll tell you why I'm using history 1, and say fine tune model now dot fit. Okay, this dot fit is what is actually going to train our model. So how do we train our model? Inside this dot fit, I'm going to say the data gen that we did dot flow. Okay, X train, I'll explain this also. Y train, then we set the batch size. I'm going to give it 32. What I'm doing here is that you remember what we did to the training dataset. We have generated some images, data generator. We have generated some images of our training dataset, where the images are rotated, the images are flipped, the images are randomly shifted horizontally, vertically. We've generated some images over here from our training dataset. Now we want to train our model on these. We want to train our model on these images, okay, plus what we already have. And now we will be taking these images 32. So the batch size 32 meaning that the images are a lot. Let's say we have 5,000 or 50,000 images. We can't train all these 50,000 images at once. What we want to do is that even from this image, the image data generator, the image that we have generated, we don't want to take all of them at once. We want to take them in batches. So we take 32, we train, we come back, we take another 32, and then we train. So that is what we'll be doing. You take, you train, you take another, you train until you train all the data. Now we have something called the validation data. Now this validation data is what we'll be testing our model on. So it is X test and Y test. We'll be testing our model on this. So after we have trained our model on all the training data sets, now we have to test our model to see how well it is performing. Is it able to predict that this image is a cat, this image is a dog, this image is a this image is a that, based on the number of classes we have? Is our model able to predict properly? So that is what is contained in this validation data. Validation data. All right, and then we set the number of epochs. Just for resource reasons, I'm going to use 20, and then I'll set the batch size to also 32. Now let me explain what this here means. So let's go back here so that I can get a better way to explain it. We have a data set, the CIFAR data set, which consists of over 60,000 images. We divided it into training and testing, which is 50,000 and 10,000. Now from the training, we are going to be taking the images in batches. So 32, 32. Once we're able to take all the images in the training, we call it one epoch. So if I say the epoch equals 20, it means that we are going to train all the data in this data set 20 times. We are going to take them in batches 32, 32, 32 for all the images, which becomes one epoch. Do it again for a second epoch. Do it again for a third epoch. Now do this for 20 times. Okay, then afterwards we have the testing. So it is taking them in batches. And also for the data that we generated, it is also going to be taking it also in batches, which is of 32. So that is what it actually means. If I take all the images in the training set 32, 32 in batches of 32, and I take all of them, I train all of them, that is one epoch. If I do it again, that is epoch 2, epoch 3, epoch 4 till the last epoch. Alright. Now the last thing I want to do now is to plot. I want to see what is actually going on. I want to plot the data so that we can actually see what is happening. So we are going to plot. That is why I actually included matplotlib. So I'll just say something like plot the data, and then to plot it we say plt dot plot, and then history. Remember I said history 1, right? And then history. Now the reason why over here I use history 1 and not history is that this fit is going to produce an object called history, which is what we are using over here. So I just wanted you to know the difference between the history we created here and the history this fit is going to produce, which is from here. So from the history that our training is going to produce, we want to know from it the accuracy of our model. The accuracy. So we can add some labels if you want. So I can just do this, and let's say dataset name, and add something like train accuracy. So the accuracy of our training. Yeah. And then maybe I can just copy paste it here and change a few stuff. Like this is going to be the validation accuracy. So the testing accuracy, we want to see the accuracy of our testing data. Then I'm going to change this to validation accuracy. So the testing is also called a validation. You want to make sure it is valid, that after we train the data on the training data or the training data set, when we tested it, what accuracy did we get? Were we getting the accuracy we were expecting? So that is what this actually, the testing here is also the validation. So that's the validation accuracy I'm doing here. So I just copied pasted it. History 1, from the same history 1, the history, the val accuracy, the label, the data set, and the validation accuracy. So we are going to do something, say plt dot and get the label, the x label, sorry. And let's pick the epochs. Remember we are running it for 20 epochs. We want that one to be the x axis or the x label, and plt then the y label. We are going to take the accuracy. We want to see the curve for the accuracy, how well our model is performing. Then you do just the basic stuff, which is plt dot legend, right? And then plt dot show. Good. So I think now we can actually say we are done with the function for our tree model, which is quite a lot, and I can see it's quite a lot. We started from the input, went to the base model, then went to the fine-tuning, which is clearly here, the input, the base model, went to the fine-tuning, then we had to build our own fully connected layer, then we built our fine-tuning model, which takes the base model as its input and then the output as our fully connected layer, which is X. Then we had to compile it in case of errors, and also to compute for the accuracy, and to get the to compute to optimize our model, the metric to measure the accuracy, and also to use the error to better make our predictions. Then a data generator is to add some data augmentation to our model, which is, twist the images, rotate them, and then produce several images and add them to our training data set. And then once we have them, we are going to train our model on it. And also we are going to now fit our model itself, which is we are now going to train the model itself. So we are going to train the model on our X and then our Y, and then our bar size being 32. This is from the data that we generated, but the bar size for the entire data set is also 32, and we're running for 20 epochs. As I explained epochs over here, that if you take 32 from the data set and we are done with all the images in the data set, that is one epoch. So we are doing this 20 times, right? And then the validation data is the X test and the Y test. We want to see, can our model really predict that this image is a cat, this image is a dog, this image is a horse, or this image is a truck? That is what the validation test does over here. So I think I can add here that some data augmentation just to make it clear. And then here I can also add that we are fit. I can just say fit, right? So that we are training our model, and here we plot everything so that we can actually visualize what is going on. Good. So that will be it for the train function, or the train model function. We are actually done with the train model function. Currently we are done defining our two functions, that is load data set and train model. So in the next cell we can call our train model and then pass in what we need to pass in, which will be the data set name. In this case it is CIFAR10. So we are going to pass in the data set name in here as CIFAR10. Alright, so before we run the cell to train our code, let's look at a few things here. So make sure you have your inputs on point. In your load data set, make sure your indentation is on point also, because indentation in Python is very important. Note that we have if else, and the data pre-processing and the one-hot encoding are outside the else statement, not inside it. So make sure you do the proper indentation for it. Also in the train model, make sure you have the proper indentation as well, just as I have here, very well structured indentation. Now, one thing I would like to point out is, if you remember during defining of this train model, I talked about something called hyperparameters, and I said there's this thing called the learning rate, which is a hyperparameter. So a hyperparameter is something that you actually do not know beforehand. Before training the model, it's a value you do not know. So you start with a random value, which is generally a very small value, and then you twist and perform some experiments to adjust it to see how well it fits your model. So you keep adjusting it to see which value will fit your model. So initially I passed in this value here, which is 1e -4 or -4, which is 0.00001. Okay, very small value. I realized that this was not a good value for our model. So I performed some other experiments by using another value, which was 1e -5, which is 0.00005, sorry, 1, a smaller value. And I realized that that is also not that too, it's good but not too good. So I tried another one, this one here, which is 0.0000001. Okay, so I found that this was a little better than this one. So to find one that is well balanced, I just picked the middle value between this here, this value, and this value. I just picked the middle value between them, which is 0.000055. So what is what I have here? 5.5 e -6, which is 5.5 times 10 to the power -6. Okay, so a very small value for the learning rate. So the learning rate is a hyperparameter. It is very important when you are doing this work here. So I talked about you performing experiments. So TensorFlow has a playground where you can perform this experiment by twisting your learning rate and adjusting it to see how well it performs on your model. So you can try that out. So again, hyperparameter, a value you do not know, you have to try out some values to know which one it works. This part is purely experimental. So that is the only thing I'll point out here. And then make sure everything is well structured just as we have, and then we can now train our model. Now, one thing I didn't tell you is that in the course of when I was writing the code, I actually turned off my GPU to use the CPU so that I could just have time to do the coding. So now I can just go back and switch to GPU, okay, and save. So now I can just rerun the cells. If this was something you also did, you could just do that. Switch back to GPU, and also you run this cell, and then you run your train model function, and then lastly you train the model. So this could take probably around 10 to 20 minutes if you're using a GPU, but with a CPU it probably could take you days to train this model. So I strongly advise you use the GPU to do the training. So I will get back once all the epochs are run. We are running 20 epochs. After they are done, I'll come back and then we go through the data that we are going to. So after 80 minutes, our model is done training and it's also done testing. So as you can see over here in the history that was returned, we have accuracy, loss, val accuracy, and then the val loss. The val accuracy is the testing accuracy. So the testing of our model after it was tested by our test images. So that's what we call the validation accuracy, the val accuracy. So if you move down to the last epoch, that is epoch 20, we can see that the accuracy of the training data set was 84%, and that of the testing data was around, the testing was 83%, which is quite good. So if you also look from the graph to see how it was, we have the train, which is the blue, and then the validation, which is the orange, and you can see that they all kind of converge over here at around 0.8, which is not too bad. So you can actually work more on this project to make it more accurate, that is to increase the validation accuracy. As I said, the validation accuracy is after our model was trained, it had an accuracy of 0.8, and then after it was trained, we tested the model with test images it has not seen before, and after it was tested, we were able to get the accuracy to be 0.83, that is 83%, meaning our model, if it has 10 images, is able to 10 images it has not seen before. Out of the 10, it's able to predict accurately 8 of these images and 2 possibly wrong. So it's able to predict that this is a cat, this is a dog. Out of 10 images, it gets 8 right, and then probably the 2 remaining will be wrong. So we can actually also improve this model so that it could be more accurate when it is tested against images. So for now, our validation accuracy is 0.83. Right. So that is basically it for the fine tuning, that we train our model and then we test our model to see how well it performs when it is tested with test images, which we now know for it to be 0.83. So I'm going to leave a copy of this project on my GitHub. So if you want to have access to this notebook and this project and this code and everything, I'm going to put it on my GitHub. I'll leave the link to my GitHub down in the description for you to just go there and then download the file. So we started a long way from building this project, loading a data set, training the model. So this is basically what transfer learning is. You taking a base model and then you fine tuning it. So from now, I'm very clear that anyone who went through this project will be able to just pick any AI model and be able to fine tune it. And I'll be happy if you are. So that's basically it for this video. If you are new to my channel, I will really appreciate it if you do subscribe by hitting the subscribe button, and then turn on your notifications so that you get updated anytime I make a new video. From time to time, we'll be making more videos on AI, that if that is something that interests you. And be sure to hit the like button to help with the YouTube algorithm. Yeah, so thank you for sticking with me throughout over an hour-long video and learning something. And I'm sure you probably have learned something on transfer learning and being able to pick an AI model and fine-tune it. So thank you for your time. Merci pour votre temps. Au revoir and à bientôt. See you. Bye bye.